All right. So we're going to keep talking about damage accumulation. And we ended the last lecture by using an iterative process to calculate the damage accumulation in the example problem in Chapter 8, which was this cylindrical bar which had fully reversed loading at the ends, but it had 3 phases and it had a spectrum of loading in time. So we ended on this slide here, which showed for each load level, what the stress is, given an area of 0.15 inches squared. The number of cycles a specimen is expected to last at that stress level. And then we compared that to the number of cycles that we had in our loading, and that's the cumulative number because the order doesn't matter. I had to amend the middle number there to 21,000 because that was an error. But the ratio here is correct, and so the sum of the damage is 0.85. We had a brief discussion before starting this lecture here in class about this particular SN curve or data that we're using and where this falls in the procedure of solving fatigue problems, specifically with respect to the Marin factors, right? So when we have much simpler situations, or when we prefer to consider our situation and simplify it down to one of those simpler cases, then we use the Marin factors to modify our endurance limit. We just say, okay, it started out at this level, I multiply all my factors together, and now it's at whatever, 50% of what it was, okay? The SN curve that we're given for this problem already includes 99% reliability, and so we're also going to assume that it includes axial loading, and we're going to say that the size factor is not that important, nor the surface finish factor. And so the Marin factors are for much simpler problems, and so you would not use all of the points along the SN curve and then subsequently modify the endurance limit at the end. So don't use the Marin factors after doing this kind of damage accumulation. See if you can get the best SNP curve first before you do that. Otherwise, you could take a problem like this, and if you only had sort of undergraduate level knowledge, you'd have to choose. You'd have to say, okay, well, I'm just going to choose the highest stress, right? And I'm just going to look at this level and assume that this is really what's contributing to the majority of the damage. So I'm just going to use the Marin factors to modify the endurance limit and then calculate a diameter from that, right? That would not be that far off, considering that phase of loading contributes to 80, actually more than 8. So it's 80 divided by 85, right? So most of the damage is contributed by that phase. So if you were going to take this specific problem and simplify it down to kind of that level, then you would look at it and you'd have to use your now graduate level intuition to say the second and third phases don't really contribute that much, based on what I know about cumulative damage theories. Okay, so that's one theory. And then we're going to cover one more important theory today, and it's called the Henry cumulative damage theory. Okay. And this theory was proposed to not just drop the endurance limit by applying Marin factors or something like that, but actually to shift the whole SN curve down and create or define a damage fraction by how far that curve is moving down, okay? So let's say for some level of reliability, right, you had an SN curve, that's just the standard one. And then you applied some stress to it. Let's call it S1, some initial phase. And you applied this amount of cycles to it, right? So we know how to apply the linear Palmgren-Minor rule. We go over and look at how many cycles it would last at that strength, and then we go forward from there. In this case, we are going to do something a little bit different, and we're going to define the cycles that we have. We're basically going to say if we have this many cycles, then at any stress level that we could choose, let's say like S2, S3, et cetera, we would have some number of cycles left, right, at those loads. And so we could come up with a definition for shifting that curve down and looking at where it hits this 10 to the 6th cycles, or whatever we're defining as kind of an infinite life. And so we could say, if we keep drawing these curves, that if we build up enough damage, then the endurance limit, right, SE prime, is going to drop to 0, right? It's going to totally disappear. The curve is just going to like crash into the x-axis. It's going to keep going down. And so that is Henry's hypothesis, right? So instead of defining a damage ratio in numbers of cycles, we're going to find a damage ratio as kind of how much the endurance limit has dropped. So in the book, they show it like this. They say damage is equal to the original endurance limit. So instead of SE prime, which is from the undergraduate textbook, they have E naught. Then E is our modified endurance limit, and we'll just say it's normalized by E naught. So in this case, D is damage, we already knew that. E naught is our original endurance limit, or in some cases, the original fatigue strength, right, at some sort of high number of cycles for like a non-ferrous alloy. And then E is our modified endurance limit. Okay. The book does not give a detailed derivation here, and so I am also not going to give a detailed derivation. But you can see that the new endurance limit, which I'll sort of draw right here, if this is E naught, is lower, and it is defined where the shifted line meets this 10 to the 6th cycles, and then it's the intersection of those two things. Okay. And so then we can think about sort of the combination of n, little n, how many cycles we're applying, right? Big N, the number of cycles it's expected to last, what stress we have applied, and then those are going to combine to give us our modified endurance limit E, okay? And so I'm going to write the equation here, and then I'll write a box around it so it doesn't get lost on the slide. So our modified endurance limit is whatever stress we had applied times 1 minus the cycle ratio, n over n. And then in the denominator, we have basically how far we are above the initial endurance limit. So S minus E naught divided by E naught plus 1 minus the cycle ratio again. just draw a box around this. Okay. And if we wanted to go back and calculate the damage ratio from that, we could take this E and plug it into here, right? So there's another expression in the book. But we don't really, we're not going to use that damage ratio and see whether it sort of adds up to 1. Rather, what we're going to do is an iterative process of changing the endurance limit. And if that endurance limit goes down to 0, then we've modified it too much and it cannot withstand the cycles that we've applied. So let's go back to our example problem and use this where we apply our first phase and then we modify the endurance limit, and then our second one, and then our third one. So one benefit to this analysis is that it is not agnostic to the order in which things and the order in which the stress levels are applied. Right? So we're not just going to say at the beginning that we're doing 3,600 cycles at the highest stress level. We're going to say we're doing 1,200. Then we go to the next, then we go to the next, and then we see how we come out. Okay? So let's make a chart to keep track of that. So at the beginning, we will have our initial endurance limit. So that was, let's put it in kpsi. So that was 68. Okay, and then we're going to apply our first load, right, which was 22,000 pounds. And let's use an area that is approximately what we had before. So for this, it's going to be a constant. I'll write it in the corner instead of taking up space in our table. So area, I'll write it on the bottom right so it won't get in the way. Okay, area is going to be 0.148 inches squared. So we're using the same sort of area that we came out with at the very end of the last analysis. So this will help us to prove whether the order matters. Right, so then we have the load, area, so then our stresses for this one are going to be 148.7 kpsi. So that was pretty high. And at that stress level, we had 1,200 cycles, and the allowable number of cycles at that stress level is 3,800. Okay. All right. So our n over n, that's a helpful ratio for that equation that we had on the previous slide, is 0.316. And this is not going to just sum like we did before, but rather we're going to use it to calculate the modified endurance limit. The next ratio that's helpful is kind of how far above the original endurance limit we are, right? So S minus E naught divided by E naught. So we're at 1.19. Okay, so then we can combine this 0.316 and 1.19 in the equation that we had before. I'll repeat it here on the bottom. S1 minus n over n. S minus E naught divided by E naught plus 1 minus n over n. Okay. So now if we calculate an updated E naught, it's going to go back into the first column of our iteration. And it's going to be 54.5 kpsi. Okay, so now we move along in time. So when we enter now our second phase of loading, our second load level for the first block, we have a reduced endurance limit. All right, so now let's go through and do the iterations again. So our load level is load B, it's 12,000. Our stress is going to be 81.2 kpsi. And if we have that stress level, it would be expected to last, 160,000. And we are applying 7,000. Okay, so n over n, quite low now, 0.044. Okay, so this does not, I mean, if we were thinking about the linear damage, we can look at sort of the ratio of these. So this doesn't really contribute as much, but it does contribute. And now how high we are above that, at that stress level, is we are lower. Okay? Yes?
Is the E not the new 54.5 or is it still 68?
So the new E naught is the new one. It's 54.5. So we're going to use this E now for everything moving forward there. Let me just make sure that's right. So S, so n over n is equal to 7 over 160, so that seems right. And then S, 81.2 minus 54.5 divided by 54.5. So it's like 27 over 54, yeah, about half. Okay, so then we're going to use these ratios to recalculate the endurance limit. It's going to drop a little bit more, but not really much, so it's going to go to 53.2. Okay. And if we wanted to, for each of these, I'm not going to do it, but if we wanted to, we could calculate the damage, right? Because the damage was just defined as kind of E naught minus E divided by E naught, right? So we can see as a fraction how much our endurance limit is dropping each time. Okay, so now it's 53.2. Now it gets hit with that very long segment where we have a lighter load, but it occurs over a very long time period, right? So now our load is 6,500. Our stress is pretty low. It's like 44 kpsi, which is below the endurance limit, even the modified endurance limit. So that means it's expected to last a long time. And even at sort of 50,000, right? We have 50,000 divided by infinity, we get 0 here. And then if that's 0, that's 1, that's 1. I don't think it changes at all, right? So our endurance limit is going to be the same. And this aligns with what we said before for which phases are contributing more to the damage. We said that the third, even in the linear rule, that one always fell below the endurance limit, so it doesn't contribute. But we've only been through one of the 3 blocks of this loading. So now we keep going. Now we apply the highest stress again. So we have a load 22,000, right? This would be 148.7. Okay. And we'll have the same now we have a modified endurance limit and the whole curve is shifted down, okay? So our expected number of cycles that this is going to last is less than it was before. So before it was 3,800, okay? And now it's going to be 1,400 because the whole curve has shifted down by about 15 kpsi. So if we keep the same slope, this is what it comes out to be. Okay, a number of cycles is the same. 1,200. Now we have 1,200 divided by 1,400, so that's a pretty high ratio. So n over n is 0.857. And our ratio here is 1.8, okay? So we still have life left after this, right? So the n over n doesn't make sense. You can see that it's adding up to more than 1 now, right? If we were using the linear rule, then this would have already failed, okay? So if we now calculate a new modified endurance limit from this, it drops off precipitously, goes down to 10.95. We started at 68, now we're at 10.95. And we are on the second load in the second block, so let's do that calculation now. So it's 12,000 here. Stress is the same, 81.2. Number of cycles it's expected to last drops off significantly, which is now it's only at 8,000. Okay, because now our entire curve is shifted down 58 kpsi on that axis. So we dropped from being able to withstand 160,000 cycles to 8,000 cycles at the same applied stress level. And we're applying 7,000, so 7 divided by 8, 0.875. And this ratio is going up real high. It's like 6.4. All right, so if we modify this again, it's going to keep dropping. It's actually going to go to 1.55. Maybe we can hack it, maybe we can't. So we'll keep on going through and see. Load is 6,500. Stress is 44. Uh-oh, that doesn't look good. If we are applying 44 kpsi and our endurance limit is 1.55, that's not expected to last very long. It would be expected to last, I think it like just hits it, 50,000, and we are trying to apply 50,000. So okay, so our n over n is now 1, right? And then we, if n over n is 1, then our whole equation kind of collapses, right? Because our new modified endurance limit is 0. So we didn't make it. We made it through the first 2 blocks of the loading cycle at this cross-sectional area, right? And so what you want is kind of that modified endurance limit to come and keep dropping until it hits 0 right at the end of your last loading segment. So the conclusion from this is that the area is too small and a new larger area has to be tried for the next iteration. Okay. And so it's going to get a little bit messy if we try to do it. And so I was not planning on covering that today. Okay. Yeah. Ask one more time.
How do we get that n value? Because it changed after the endurance limit changed, right?
This one?
Yeah, those values.
So those are read from the modified SN curve. Let me think about that for just one moment. I think the best approach to getting these values would be to look at the SN curve that we were given initially and then write an equation for that slope. And then you just move that slope downward. So I can draw that on the next slide. The question is, where do these n values come from? Right. So if I go back and draw that initial curve, right? I can take the values from the initial curve and then calculate what relationship there is here. So we can say that our fatigue strength is equal to some constant times the number of cycles to some power, because it's a straight line on a log-log plot. And then this A value right here is what determines where it falls on the y-axis, right? So if our endurance limit, let me just think about this. So if here's the 68, let me go back to the prior slide. Okay, then it drops to like 54.5, right? Yeah. So I'm just going to draw that here, right? So it drops to like 54.5. And then the slope here is the same. Right, and so the slope there being the same means that B is the same. But A is going to change, right, just based on where it falls on the plot. So the iteration on the other, on the table that we had says that these first three values, I'm just going to sort of put a box around them. These first three values are from the initial SN curve. Let me think about that. Nope, maybe the second one is not. Second one would change, yes. Let's undo that. So only the first value is from the initial SN curve. So just this 3,800. And then so we would take the initial SN curve and fit that, or just read it off the plot and come up with that value. Then we modify the endurance limit and it goes down to 54.5. And that gives us a different point to use, right? So now we have 54, we have 10 to the 6, 54.5 is that point now. But B is the same. So now we can determine kind of any other points along that line that we want to. We could resolve for A, right? If we know that 54.5, right, K PSI equals A times 10 to the 6 to the B, right? Actually, all this is to the B, yeah. So you can resolve for A, and then you have this equation for your second line of iteration, and for some stress level, you find N. Does that make sense?
Does the upper limit also change?
So there's some contention about that. The question is, does the upper limit change? In the textbook, there is the Henry theory, which is what we're working with now. And there are some observations that this can be a good theory. Like if you tried to regenerate this whole curve after you accumulated some damage. However, the ultimate strength of the material doesn't change. So we still have this point up here. And so there is a second modification, or a modification of this theory that actually connects that new endurance limit with the ultimate strength, modifying the slope slightly. But this is a subtlety that's, I don't think, important to cover in the class, but there is some contention about what happens here at this end. Yep. So we're mostly focusing on sort of what's happening down here. Maybe some higher stresses up here, but we're just going to assume that the slope stays the same so we can estimate how many cycles it will last at that stress level. All right. Other questions? Okay. So just to close out today, to sort of summarize what we've done in the last couple of lectures, we learned about a linear combination of damage fraction based on number of cycles. That's the Palmgren-Minor rule. And that's a good first pass, right? That can give us order of magnitude on design sizes and things like that. But if we really want to be more exact and care about the order in which the load spectrum is applied, we should use a better theory, such as the Henry theory, and an iterative approach to come up with some dimensions that are going to withstand not just the total number of cycles, but rather that total number of cycles in the order in which they are experienced. In the next class, we're going to cover one final theory, which is the, hang on one moment. It's the Manson double linear damage rule. So we're going to learn that one. And then we'll talk a little bit more about fracture mechanics and how cracks propagate. Because this damage accumulation still assumes that there is not a specific crack that we're following. This is kind of just a theoretical damage accumulation until a gross failure point. Okay? But if a crack is actually observed and we know the size of it through some inspection protocol, then there can be a little bit better calculation of that crack propagation. And then finally, when we talk about different types of loading, we'll learn some methods for thinking about the highest stresses that are applied in time. One of those is called like a rain flow counting method. So that's a fun graphical technique. So I'll end there for today, and I'll see you all on Tuesday. I will be available over the next few days for any questions that pop up on the discussion board. I did post the second problem set, and then I believe the first take-home exam is scheduled to be released next week. And so you can expect that to be based on some of the homework problems, but to ask you to apply knowledge to some new problems. All right, thanks everybody.